Okay, so we're going to be covering a test for convergence of infinite series called the integral test. So recall that the primary question when dealing with an infinite series is, does it converge or not? And remember that the essence of that question is, do these terms, a sub n, race to zero fast enough so that the sum is finite? We will cover many different tests to answer that question. And one test is the integral test. And the idea here is we will tether the series to a related improper integral. So here's the formal statement of the integral test. And the key thing here is to think of the series and this improper integral and the fact that they are tethered. So we have sort of the usual setup. We have an infinite series. The terms are all non-negative. But then we have a non-negative function for x greater than or equal to 1, and here is the tethering. So for any n, a sub n actually sits on the function. If that's the case, then the conclusion is both the series and the integral have the same behavior. They either both converge or they both diverge. So this is a little bit more intuitive when we draw a picture and see how it works. So here's the graphical interpretation. So suppose you have this set up and we have the graph of y equals f of x. And then we're going to look at our a sub n, and remember the idea is they are tethered. The a sub n, maybe we'll do these in blue, the a sub n are tethered to the function. So here we have a1, a2, a3, a4, so on and so forth. And let's think about our improper integral. So the integral from 1 to infinity of f of x dx. And let's say that this is this black area. So we remember from doing that section in the course that that improper integral represents the area drawn in black here below the curve y equals f of x over the interval 1 to infinity. And now we are going to look at this related sum, n equals 1 to infinity of a sub n. And we can also interpret this sum as an area. So think about this sum as, why don't we say, a right-hand rule approximation to this improper integral. Now, with this interpretation, think of here, what's the width of that interval? The width is 1. So the area of one of these rectangles is the height, which in this case is a1 times the width. So the area of this rectangle is a1. Similarly, we can argue that the area of this second rectangle is its width, which is 1, times its height, which was a2. And hopefully we can see the pattern here. To get the areas of all these rectangles and add them up, that is exactly this infinite series here. And what the integral test says is that these either both converge or both diverge. One natural way to think of this picture, well, you have this tethering, and you can think of it as the blue area is an approximation to the black area. And because of that tethering, they're either both finite or they're both infinite. If they're both finite, they'll have different values, because in the way we've drawn here, the infinite series looks like it would be bigger because it's an over approximation. But the key is that they're either both finite together or they're both infinite together. We could have drawn this same kind of picture going the other way with the rectangle. So if we draw the same sort of function, and we're thinking of the same area computation for the improper integral. So remember, that's this area here below y equals f of x over the interval 1 infinity. Well, we could have gone a different way. Instead of a right-hand rule, we could have, say, done, why don't we do it this way? A left-hand rule. Now we still have the same tethering. Here's A1, here's A2, A3, A4, A5, so on and so forth. But pictured this way, the orange area would be, you have to sort of imagine that you can throw out this first rectangle because that's not relevant to the approximation of the black area. But that won't affect the fact that both converge or both diverge together. So this is the idea. Here now you could think of the orange part, the orange area, minus this first rectangle. So that would really be the sum from 2 to infinity of a sub n. But you can think of that orange area as an under approximation to the black. So if the black area is finite, it forces the orange area to be finite, because the orange area, again, leaving out this first piece, the orange area would be smaller. So the finite black area being bigger than the finite, or bigger than the orange area, means the orange area is finite. Conversely, if the orange area is infinite, it causes the black area to be infinite because the black area is bigger. And you can make similar arguments up in our first picture. If the blue area here is finite, well, the black area is smaller, so it's also finite. Similarly, if the black area is infinite, well, the blue area is bigger, so that's also infinite. So this is the idea. These two pictures are really the key to understanding the integral test. But the bottom line is that when you have this tethering, the series being tethered to the the function f of x, then both the series and the improper integral will exhibit the same type of behavior, in that they either both converge together or they both diverge together. Again, if they both converge, they won't have the same value, simply because just looking at in either of these pictures, the blue area and the black area differ, the orange area and the black area differ. They won't have the same value, but they will both be finite together or both be infinite together. So let's kind of dig in here and see some examples. And so a very natural first example to look at is our harmonic series. So we've looked at this series before. We've actually mentioned that it does diverge, but we haven't seen it yet. So we use the related integral from 1 to infinity of 1 over x dx. So noting here that to sync up with our statement of the integral test, if f of x is 1 over x, f of n is then 1 over n. And so this is the appropriate function that our terms in our series are tethered to. So it's essentially, if we draw it, it's really the same kind of picture that we have in the previous slide here. Okay, so that being said, we work through this integral, and remember, we actually have already seen how we do this, but we write this as the limit as t goes to infinity, integral 1 to t of 1 over x dx from our definition of an improper integral, and we know this is the limit as t goes to infinity of the natural log of absolute value of x between 1 and t, which is the natural log absolute value of t minus the, now wait, we need our limit. This is the limit as t goes to infinity of natural log absolute value of t minus natural log absolute value of 1. Natural log of absolute value 1 is, of course, natural log 1, which is 0. Our t is positive, so we can drop the absolute value. This becomes the limit as t goes to infinity of natural log of t, which we know is infinite. Because this 1 over n term is tethered to this function, and we now know, we know that the area below the curve of y equals 1 over x from x equals 1 to infinity is infinite. This means, by the integral test, that the sum from n equals 1 to infinity of 1 over n also diverges. So this is how we see that this classic example of the harmonic series is a divergent series. It's because it's tethered to this related improper integral. So there's one example. Another example is to think about the sum of 1 over n squared. And we take a very similar approach here, and we look at the integral from 1 to infinity of 1 over x squared dx. And recall, we can go through it, but you can cite at this point that this converges because the power 2 is bigger than 1. So remember, that was our rule, that if you have the integral from some positive value to infinity of 1 over x to the p dx, the integral converges if p is strictly bigger than 1. So this is a convergent integral. We can go through it. If you forget the rule, you can always just compute the integral. So we use our definition, well, our framework for handling improper integrals as usual. This becomes the limit as t goes to infinity. When we do an antiderivative, we have minus 1 over x between 1 and t. When we evaluate, limit t goes to infinity, minus 1 over t minus a minus 1 over 1, which is the limit as t goes to infinity of 1 minus 1 over t, this 1 over t term approaches 0, so the whole thing is just 1. So because this improper integral converges and this series is tethered to it, the integral test tells us that our series also converges. Note that we do not know the value. All we've found here is that it does in fact converge to something finite. But in real life, what you might, if you were using this in an application, what you might do is, now that you have confirmation that it does in fact converge, is you approximate it on a computer. You compute a kth partial sum for some large enough k, and you get an approximation to it. So these two examples lead us into a theorem which you can cite, and we will use this a lot going forward, but it's this, we'll call it a p-series theorem. And so the series, sum of 1 over n to the p, converges if p is bigger than 1 and diverges if p is less than or equal to 1. The way to remember this is it's the same criteria as your integral from 1 to infinity of 1 over x to the p dx. And so the way that you prove this theorem is by doing this improper integral and making the argument that because this integral is tethered to this series, it has the same convergence rule. Okay, so that gives us the rule for p-series. And again, this is something that as we explore future tests for series convergence, we will cite a lot. So this is something that you want to know well. Okay, that being said, let's look a little bit further at another example. And in my experience, these are often the examples that people find trickiest. The integral test tends to be one that people tend to not think of on, say, an exam setting when doing these types of series convergence questions. Now, this is a natural integral test example, but remember, it's always helpful to first think about a series and try and get the idea of what's happening. And if we rewrite this as the sum of n over e to the minus n squared, let's go back to our race situation. Remember that polynomials go to infinity much more slowly, and let's just fix one thing. This should have been e to the n squared when we put it in the denominator. There we go. So remember that polynomials race to infinity much more slowly than exponentials. So what you have here is a sum where you have something going to infinity in the top and something going to infinity in the bottom. But the term in the bottom is going to infinity dramatically faster than the top. Remember, this is Bugs Bunny versus the turtle. So this denominator is just dusting the numerator as both go to infinity, which means these terms, this ratio, will race to 0 really quickly because the denominator is blowing up much faster than the numerator. And so because of that, it should be sufficient, these terms should be approaching 0 sufficiently quickly so that the series converges. And remember, that's always the issue when it comes down to series convergence. Are the terms racing to 0 fast enough so that the series converges? And we should expect the answer to be yes here. So that gives us the idea. Now remember, that's not the same as actually showing formally that this thing converges. But we expect it to converge. And we come back again to the integral test. and we say, let's look at f of x is x e to the minus x squared. And we can see clearly the tethering. So with this f of n is n e to the minus n squared. And so we can expect this sum to have the same type of behavior as the related improper integral of x e to the minus x squared. So we look at this integral from 1 to infinity of x e to the minus x squared. So this is the limit as t goes to infinity of the integral from 1 to t of x e to the minus x squared dx. And we recognize that we need a u substitution. U is minus x squared. So du is minus 2x dx. We need x dx. So minus 1/2 du is x dx. So this improper integral becomes limit as t goes to infinity of the integral. We have x dx, which is minus 1/2 du. And then we have e to the u. Then, of course, we have the limits to deal with, and you can do this either way. You can do this integral with respect to u, and then substitute back in to get things in terms of x and use the limits for x of 1 and t, or we can just get rid of x altogether. This is all a matter of preference. If we get rid of the x's, if x equals 1, then to get the limit for u, we plug 1 in here. And so we would get negative 1 squared, or negative 1. So our lower limit for u is negative 1. And then if we plug in t for x, we would get u equals minus t squared. So x equals t, u is minus t squared. So this integral, we will now completely eliminate x from the picture. Right? Instead of going from x equals 1, that's going to be a limit of u equals minus 1. And then instead of x equals t, we go u equals minus t squared. So now we've changed to limits for u. X is completely gone. We do not have to return to it. So we know that this integral, this minus 1/2, doesn't affect things. In antiderivative of e to the u is just e to the u. So this is minus 1/2 e to the u between negative 1 and negative t squared, which is the limit as t goes to infinity of minus, so we evaluate minus 1/2 e to the upper limit, minus t squared, minus negative 1/2 e to the minus 1. It's usually easier to make sense of these limits if you deal with just positive exponents. So we have, let's rewrite this first term. Instead of e to the minus t squared, just write it as 1 over e to the t squared. And then we have minus minus, so plus 1/2 times 1 over e. It's easier to, for most people, it's easier to understand the limiting behavior when you have the positive exponents. And for this first term here, we see that we have a 1 in the numerator and a denominator that's exploding. It's getting huge. So this term is approaching 0. And this second term here is a constant. So this whole thing is 1 over 2e. What matters is that this is finite. And again, because these two, the infinite series and the improper integral, are tethered, they have to have the same behavior. So the integral test tells us that the series also converges. But again, we do not know to what value. And that's going to be true for most of the tests that we do. The only test that we'll do where you actually get the value of the series will be the case where you have a telescoping series and the case where you have a geometric series. The other tests are all yay or nay, thumbs up or thumbs down. And here we get a thumbs up. We see, yes, by the integral test, this series does converge. But this analysis does not tell us to what value. So this is one of these tests that you want to have in mind. I think as you're learning these different tests for convergence of series, the integral test is one that you want to, when you're stuck on a series convergence question, the integral test is often a good one to think of. And the way I usually think of it is just look at the series and imagine if you have the n's replaced with x, and then think about all the techniques of integration you know from your prior calculus experience. Can you actually do the integral? That's kind of the natural way to consider the integral test.